Okay, let's go ahead and get going just because yeah, we should. So this thing here, we could compare the sum from n equals 1 to infinity of whatever n equals 4. It certainly looks a lot like 1 over n cubed. In fact, it is correct to compare this to, we want to compare it with the sum from n equals 1 to infinity of 1 over n cubed, just 1 over n cubed. And that's a good choice because we know that our sequence 1 over n cubed plus 4 is less than 1 over n cubed, regardless of our choice of n. I should say, as long as n is in between 1 and infinity, which it certainly is. So if this sequence is less than that sequence, and we know that the series for 1 over n cubed converges, then this other series of terms that are all less than that also has to converge. So we're going to compare to this convergent thing. On the other hand, for this next one, so here's what I would compare this to. I would compare this to, well, I know that 1 over 3 times the square root of n minus 1 is bigger than 1 over 3 times the square root of n. And so the series I'm actually thinking about here is we're comparing to the series from n equals 1 to infinity of 1 over 3 root n. And then I would pull out the 3 just so it looks more like something that I know is divergent. Because that's 1/3 times the sum from n equals 1 to infinity of 1 over n to the 1/2. And I think I said this before, but I'll say it again. Doesn't matter if we multiply a convergent series by a constant or a divergent series by a constant, as long as that's as long as it's a non-zero constant that you're multiplying by, the whole thing is still going to have the same behavior. If all of these terms are diverging, multiplying the whole thing by 1/3 isn't going to change the fact that it's diverging. Same deal here. If I multiplied all this by 6, wouldn't change the fact that the whole sum converges to some finite value. And then this last one I just want to throw in here because we did talk about this one last time. We checked to see if this series is convergent or divergent by looking at the integral, using the integral test, and we saw that it diverged. But there's actually a much easier way to see that it diverges. It is certainly true that the natural log of n over n is bigger than 1 over n, at least if n is bigger than or equal to 3, which it is. And since that sequence is bigger than that sequence, it is true that the sum of the sequence is bigger than the sum of that sequence. And the sum from n equals 1 to infinity of 1 over n definitely diverges. It's kind of, in my opinion, our most famous or our most often used divergent series. This is the one. If I say, give me an example of a divergent series, this is the first one I'm always going to think of. Always. It's just not the usual suspect for a divergent series. It's also called the harmonic series, in case someone hasn't said that already. That's what it's typically known as, is the sum from n equals 1 to infinity of 1 over n. Questions about any of these? So comparison test is nice because it lets us say, well, if we think something converges, we can compare it to something we know converges as long as it's smaller than it, and that shows convergence. Likewise, or similar wise for divergence. Let's write down the test just so we have it kind of fully written here. Where do you go? Are you over here? Yeah, you're over here. So this is called the direct comparison test. And it's very straightforward. It just says two things. Thing one, if your series is less than some other series, and really you can say less than or equal to, and we know that that bigger series converges, then our series also converges. There's probably some assumption about all the terms being positive. Secondly, if the series that's in question is bigger than or equal to some other series, let's say the sum of dn, and we know that that sum of the dn is divergent or diverges, then the series in question also diverges. Or as I like to say, if you're smaller than something convergent, you're also convergent. If you're bigger than something divergent, you're also divergent. Being smaller than something that diverges is not helpful, and being bigger than something that's convergent is not helpful. It doesn't tell us anything. Maybe you're still convergent, maybe you're still divergent. It's really unclear. Yeah, the last part of the sure. So here's what I say. If we are bigger than something that diverges, then we diverge. And likewise, if we are smaller than something that converges, we converge. It's very similar. Yes, 100%. Yeah, when you're talking about convergence, whether it's for integrals or for series, a lot of the same things apply, which is nice. Yeah, so let's look at a couple other examples. Yeah, in fact, let's look at, where'd you go? I have an example right here. Yeah, we'll save this one for just a second. So some of the time the direct comparison test is perfectly great. For example, let's do some numbers here, sure. For example, the sum from n equals 1 to infinity of the square root of n over n squared plus 5n plus 15. So a couple things I would think about here. Thing one, I'm looking at the highest powers. If I've got a rational-ish kind of thing, I say rational-ish because it's technically not a rational function because you have an n to the 1/2. But you've got powers of n over powers of n. I'm looking at the highest power of n over the highest power of n. So I'm thinking of this as being similar to, and I use this symbol for similar to, the sum from n equals 1 to infinity of n to the 1/2 over n squared, which is just the sum from n equals 1 to infinity of 1 over n to the 3/2. Okay. Converge or diverge? Give me a thumbs up or a thumbs down. Thumbs up, we think this converges. Thumbs down, we think this diverges. So I'm thinking, you're right the first time. It's definitely this way. I'm thinking, yeah, and also thumbs to the middle if you're not sure. It's totally fine answer to be not sure. Well, so here's what I would say. So there's two different questions happening here. So I'm asking about whether the series converges. Certainly the sequence, the limit as n goes to infinity of this sequence or that sequence is 0. But the series, this series specifically, we know this converges by the p test, or because it's a p series. It's a convergent, that's all right, I'll write it's a convergent p series, because what's p here? Greater than 1, right? P is 3/2, and that is greater than 1, which means it converges. So here's my thought process. I'm thinking, oh, by the way, welcome to whoever just joined us. Welcome, Caleb. Here's the attendance form if you need it. What I'm thinking is that since this looks pretty similar to that, it's also going to converge. And this is kind of the, I don't want to say the downside, but one of the limitations of the direct comparison test is that you have to know or have an idea of what the series is doing. You have to say, well, I think it's convergent, so I'm going to compare it to something that's convergent. And now here, it's relatively not terrible to do this because not only are we comparing to something that's convergent, but our denominator got bigger when we added these things. And when your denominator gets bigger, it means your fraction gets smaller. So it's really not terrible to say, oh, our series or our sequence in our series, the square root of n over n squared plus 5n plus 15 is definitely smaller than the square root of n over n squared. Right? If your denominator is bigger, your fraction is smaller. And so that's great. That means we can say then it is certainly true that our series from n equals 1 to infinity of the square root of n over n squared plus 5n plus 15 is less than the sum from n equals 1 to infinity of 1 over n to the 3/2. And so it converges. It converges by direct comparison. It is not in my opinion, it's not necessary always to write the test you're using to show convergence or divergence, but it's a good idea. It's a good practice to say, this is what I did. Let's look at another example. Sure. Let's look at the sum from n equals 1 to infinity of n squared over n cubed minus n plus 5. Once again, when you have powers of n over powers of n, you want to think about just looking at the highest powers. So I want you all to take a minute and think about what we should be comparing this to. Write it down. Write down, we're going to compare this to the sum from n equals 1 to infinity of what's going in there. 30 seconds. Think about the highest powers and only the highest powers in the numerator and the denominator. All right, time's up. We're comparing this to the sum of n squared over n cubed. I'm just using the highest powers. And then I'm, of course, going to simplify that to the sum of 1 over n, which we know is divergent. So that means we think this divergence. To be able to use direct comparison. Oh, sorry, I didn't mean start at n equals 1, I meant start at n equals 5. Sorry. Apologies. We're comparing it, but it doesn't matter if you start at 1 or at 5, still diverges, right? You can chop off the first 4 terms and the rest of it still adds up to infinity like it did before. We just subtracted off 1 plus a half plus a third plus a fourth. But infinity minus 1 plus a half plus a third plus a fourth, still infinity. So now what we have to say is n squared over n cubed minus n plus 5 bigger than 1 over n? Maybe, probably. It probably is because I started at 5. But if you really wanted to check, what you could use, you could do some cross multiplying. Cross multiply. I mean, this is where the direct comparison test starts to kind of suck. Because to actually use it, you have to make sure that the thing you're comparing it to is the thing you are is actually bigger than the divergent thing or actually smaller than the convergent thing. And maybe it is some of the time, maybe not always. But if we do this here, let's see, n cubed bigger than n cubed minus n plus 5. The n cubes cancel. Bring the n to the other side. I get n bigger than 5. And that's going to work out because I'm starting. That's why I needed to start at n equals 5, actually, because that's going to work as long as n is bigger than 5. Cool. So that works. So then we can say our series from n equals 5 to infinity, n squared over n cubed minus n plus 5 is bigger than the sum from n equals 5 to infinity of 1 over n. And so it diverges by direct comparison. Okay, look at a couple more, just kind of interesting. But we should move on to the next. I won't say better test because it's not necessarily better. It's just, I don't know. It's more often applicable. Let's do the sum from n equals 1 to infinity of 1 over n times 5 to the n. Ooh, now I don't just have powers of n. What I'll say about this one, to be honest, is even though we can use direct comparison here, later on, we're going to talk about the ratio test. And this is an example of one where I would certainly use the ratio test. Because generally, if you ever see something raised to the nth power or an n factorial, those are both really good times to at least try the ratio test. But I guess I'll say more generally, testing series for divergence and convergence is a lot like trying to integrate a function in that sometimes you're going to try things that don't work, right? When we did integration back in 21B, maybe you tried to use 7, it didn't work. Or maybe you tried integration by parts, it didn't work. So sometimes we have to try more than one thing. Sometimes things just don't work. Here, though, we can certainly say that 1 over n times 5 to the n is less than 1 over 5 to the n. That's true, right? This denominator is bigger, so the fraction is smaller. And 1 over 5 to the n, I could rewrite as 1/5 to the n, which means that this series from n equals 1 to infinity of 1 over n times 5 to the n is smaller than. So saying it's smaller than means I'm thinking what's going to happen. I'm thinking convergent or divergent. Right, because I'm showing this is smaller than something else. I'm trying to show, I'm at least moving in the direction of showing convergence. And it is because we know that this series from n equals 1 to infinity of 1/5 to the n is what kind of series? Yeah, it's a geometric series, and it's definitely convergent because our r is less than or between -1 and 1 is a convergent geometric series as r equal to 1/5 is less than 1 in absolute value, which means our series converges. So this series, I feel like there's a lot of writing here, but sometimes there's a lot of writing. So this converges by direct comparison with that. Sure. Something worth knowing, I think it comes up actually a lot, is that both sine and cosine are always between -1 and 1. Always true, no matter what. So someone could say something like the sum from n equals 1 to infinity of, I don't know, cosine squared of 7n plus e to the n over n cubed. And even though the stuff inside the cosine function there looks really dumb, doesn't matter. Because we know for sure that cosine squared of anything is always going to be less than or equal to 1. The reason I picked cosine squared instead of cosine is I didn't want my terms to be positive and negative. So cosine squared, we also know is always certainly greater than or equal to 0. Because you can't use the direct comparison test if your terms are going positive and negative. You can only use it if they're all positive. But then we can say, well, great, then certainly cosine squared of 7n plus e to the n over n cubed is less than or equal to 1 over n cubed. And then we can take the sum from n equals 1 to infinity, and the sum, n equals 1 to infinity. And we know that this converges. It's a convergent p-series. So this also converges. Again, by direct comparison. Okay, two more. One more thing that I think is less maybe something that we remember all the time. So cosine, sine, always between -1 and 1. Another function that has an interesting boundary is the following. So we look at the sum from n equals 1 to infinity of the arc tangent of n over n squared. Ooh, arc tangent. Arc tangent is bounded above. And yeah, it's less than pi over 2. So just as a reminder, because it's probably it may have been once you thought about arc tangent. Tangent looks like this. It's got, well, here's part of tangent, I should say. Between pi over 2 and negative pi over 2, we can take this part of tangent. Obviously, there's more of it to the right and to the right. It continues on like this, like that. But if we take just that part and invert it, right, switch x and y, you get x equal to tangent of y, and then solve for y, you get y equal to the inverse or the arc tangent of x. You're just reflecting it across the line y equals x. So your vertical asymptotes become horizontal asymptotes at pi over 2 and negative pi over 2. So we get something that looks like this. You can see, oh yeah, the arctangent function, as you go further and further and further to the right, it never goes above pi over 2. It's stuck. So that means that we can say that this series is definitely less than or equal to the sum from n equals 1 to infinity of pi over 2 over n squared. And if you don't just like saying that converges, you certainly can pull out the pi over 2 in front of the sum. Okay, oh, that's equal to pi over 2 times the sum from n equals 1 to infinity of 1 over n squared. And we certainly know that this is a convergent p-series. So our series converges again by direct comparison. One more time, this converges by a direct comparison. Direct comparison test is great, but it has some limitations. Specifically, sometimes you have to work a lot harder than you really want to find something to directly compare it to. Here's what I mean by this. Let's say we wanted to show or determine the convergence or divergence of the sum from n equals, let's start at 2, not 1, to infinity, of n over n cubed minus 1. Now, certainly, I am thinking this converges because I want to compare it to 1 over n squared, right? This is definitely similar to the sum from n equals 2 to infinity of n over n cubed, which is just the sum of 1 over n squared. And again, we know that that is convergent. Problem is, n over n cubed minus 1 isn't smaller than that, right? If we actually compare these, n over n cubed minus 1 is actually bigger than n over n cubed, which is 1 over n squared. And being bigger than something that's convergent is not helpful. So there's a couple ways to get around this. One way is just making up something. So you could show that this is less than something else. Here's what I'm going to say. I can say, well, if 1 over n squared doesn't work, maybe try making 1 over n squared a little bit bigger by multiplying it by a constant. Like I could say, well, is n over n cubed minus 1 less than 2 over n squared? Let's find out. Again, I'm going to cross multiply. I'm going to get n cubed less than 2 times n cubed minus 1. And I'm going to say that n cubed is less than 2n cubed minus 2. I'm going to subtract n cubed. I'm going to add 2. Is n cubed bigger than 2? Yeah, as long as n is bigger than or equal to this cube root of 2, which it is. The problem is, that's not really a problem. Yeah, it is a problem. I don't have that much time. Right? I don't want to spend 5 minutes trying to figure out the thing I have to multiply this by to make it so it's actually always bigger. And the good news is we don't have to, because there's another test that's going to kind of overcome this difficulty. But what I can say here is that, yes, we can show that this series from n equals 2 to infinity of n over n cubed minus 1 converges by direct comparison with the convergent series, the sum from n equals 2 to infinity of 2 over n squared. That would be totally fine. But again, I don't want to do that work every time. So what we typically then see is, well, there's something else called the limit comparison test, which I feel like we talked about with integrals last quarter. Like, I feel like usually that's not the case, but last quarter, a couple teachers were like, yeah, limit comparison for integrals, we're gonna do it. So maybe it's already been on your radar, but let's write down the test here and then we will talk about it. So here's what the limit comparison test says. We're gonna let the sum of b sub n be some other series. When I say other series, I mean not the one whose convergence we are trying to determine. And also, the limit as n goes to infinity of a sub n over b sub n is equal to some limit. Which I'm going to leave yourself a little room next. I'm going to say something after this, but we'll come back to that in a minute. So there's two results. Result one, if the lower series, if the sum of that series, if the lower sequence, the sum of that sequence or the series, if that's convergent, then the top thing series is also convergent as long as L is not infinity. Meaning L could be 0 or some finite non-zero number. On the other hand, if the bottom thing is a divergent series, then so is the top thing. as long as L isn't 0. Meaning L could be a finite positive number or infinity. Here's the way I think about this. What we're really saying here is that we're talking about how AN and BN compare to each other. So if the sum of BN is convergent, then as long as AN over BN goes to some finite number or 0, you're kind of saying, well, AN is just a multiple of BN. In fact, this was what I really want to write. We're going to think of essentially saying eventually AN looks like L times BN. Not perfectly, but if this ratio is getting closer and closer to, like, say 5, what we're saying is once you go way, way out, all the AN terms are 5 times all the BN terms. And if all the BN terms add something that converges, and so do all the AN terms. And that's totally fine if the limit is 5 or the limit is 0, right? Because if BN adds up to something and you multiply all of them by 0, well, the ANs will also add something finite. But infinity does not work here, because if this limit's equal to infinity, what you're kind of saying is AN is infinitely bigger than BN. And if BN is convergent, being infinitely bigger than something that's convergent means you could still converge, but you might diverge. And the same sort of reasoning is why we don't want 0 here. If here we're saying that the bottom thing is divergent, so it's getting probably infinitely large. If AN is something times that, well, as long as it's a positive finite number times it or an infinite number times it, it's still going to blow up to infinity. But if your limit is 0, 0 times something that's infinitely large, that's actually like one of those indeterminate L'Hopital's rule kind of forms that we don't really know for sure what's going to happen. So often the way people kind of say this is when you do this limit comparison thing, the series have the same behavior as long as the limit is not 0 and not infinity. And then if you're looking for convergence, 0 is okay. If you're looking for divergence, infinity is okay. That's another way I often think about it. So back to the one we were looking at before, we were looking at the sum of, I lost it. Where did you go here? N over n cubed minus 1, which we already know converges, but I would do a limit comparison, the limit compare to the sum from n equals 2 to infinity of just n over n cubed, which is 1 over n squared. Yeah.
For number 2, it says B of n diverges.
Oh, good catch. Yeah, thank you so much. That is incorrect. Yes, please, yes. Sorry about that. Yeah, they should be doing the same thing. So just like with the regular direct comparison test, we still have to have an idea about what our series is doing. If you're like, oh, I think this is convergent, so I'm going to compare it to something that's convergent. And really, I'm just using the same idea in that I'm looking at the highest power on the top and the highest power on the bottom and slimming it down just to that, and then seeing what that does. So to actually do this, we're going to take the limit as n goes to infinity of the unknown series sequence divided by the known series sequence. I almost always skip this step and just say it's going to be the limit as n goes to infinity of the unknown thing times the reciprocal of the known thing, because you're always going to end up there anyway. And then this becomes the limit as n goes to infinity of n cubed over n cubed minus 1. And what's that limit equal to? Just 1, right? Usual rules of highest powers being the same, quotient of the leading coefficients, which is not 0 and not infinity, so we're good to go. So we can say that this converges. Convergence by limit comparison. Cool. Let's look at a few more examples. I will say the limit comparison test is a test I almost always use if I have the series where I just have powers of n over powers of n. For other things like factorials or something raised to the nth power or other things like that, then I start to use other tests. But specifically, if I have something like this, the sum from n equals 1 to infinity of, say, like the square root of n over 5n plus 2, I'm just going to say, well, I'm going to do a limit comparison with the sum from n equals 1 to infinity of the square root of n over n. I don't even care about the coefficients. I just care about the highest powers. So that means, since I'm comparing it to the sum from n equals 1 to infinity of 1 over n to the 1/2, I am looking for convergence or divergence. Right, this is a divergent P series. So that means we're trying to show divergence because we're going to compare it to something with divergence. So then we're just going to do the limit as n goes to infinity of the unknown series sequence. And instead of dividing by the known one, let's just go ahead and multiply by the reciprocal. Right, this is our an divided by bn. There's an, there's bn. But I did an times the reciprocal of bn instead, because I just don't want to write out a million things all the time. And you won't want to either, right? You'll be like, especially when we get to the ratio test, that's especially where you're like, I really don't want to write this big thing over this other big thing. I'm going to skip that step and multiply by the reciprocal. And here the same thing ends up happening. We get the limit as n goes to infinity. N to the 1/2 times n to the 1/2 is just n over 5n plus 2. And you're going to get a limit of 1/5, which is not 0. So we're good to go. So we're trying to show divergence. The only limit that's not good is 0. So since this is not 0, we're on top. We say, yay, our series diverges. By limit comparison. What I'll say about this test in general is that whenever you're doing it, it's always going to, if you're doing it for this kind of series where you just have powers of n over powers of n, it's always going to work out like this. You're always going to multiply by exactly the thing that makes it so the highest power on the top and the highest power on the bottom is the same. And then you're literally just comparing those leading coefficients. And you're getting 1/5 in this case. Sure. That's a good one. I like that one. Yeah, let's look at this one. How about the sum? So sometimes it's useful for other things, like the sum of sine of 1 over n squared. You know what I should have been doing this whole time? I mean, not really, but kind of. I should have been checking to make sure that the test for divergence doesn't just show me it diverges. So if I look here real quick, if I do the limit as n goes to infinity of sine of 1 over n squared, what do I get? Sine of, and what sine is 0? Yeah. So it doesn't tell me anything, but it's something I should be checking, specifically because I've definitely seen the teacher put this series on a test before. And it really stumped a lot of people until someone was like, oh, wait, the limit as n goes to infinity of cosine of 1 over n squared is cosine of 0, which is not 0. So this one definitely diverges right off the bat by the nth term test or the test for divergence. So make sure you keep that in the back of your head. The test for divergence should always be something, I mean, really technically it's something we should always think about checking. It's just that most of our examples usually don't diverge by it. So we can move on. Here, I'm going to do a limit comparison with sum from n equals 1 to infinity of 1 over n squared. Okay. So we do that. I should also point out, just in case you were curious, if I plug in n equals 1, I get sine of 1. Sine of 1 is positive. And then as n gets larger, right, 1 radian is in the first quadrant, so we're positive. And then as n gets larger, the values get smaller, so the angles get smaller, so the sine values are still positive. Something I was like, oh, sine can be positive or negative, but not with these inputs. So if we do this, we're going to do the limit n goes to infinity of sine of 1 over n squared over 1 over n squared. Which I wouldn't, normally I would flip and multiply, but not here. What's this limit? It is 1. How did you know that? I mean, not that you have to explain yourself, but I'm just, how did you know? If you don't mind.
Sine x.
Right, it's sine x over x, and specifically, where is x going to? While n is going to infinity, but the stuff we're taking sine of is going to where? Right, it has to be going to 0. That's exactly it. We've got sine of stuff over the same exact stuff, and both of the stuffs are going to 0. Alternatively, if you don't like doing it that way, totally fine. You could use L'Hopital's rule. This is a 0 over 0 type of limit. And we can use L'Hopital's rule and get that the limit as n goes to infinity. The derivative of the top is going to be cosine of 1 over n squared times the derivative of 1 over n squared, which is negative 2 over n cubed. And the bottom of the derivative of 1 over n squared is negative 2 over n cubed. And those exactly cancel out. Good times. So those cancel. And you get the limit as n goes to infinity of cosine of 1 over n squared, which is exactly cosine of 0, which is 1. Which is not 0 and not infinity. So we know that whatever this one does, that one does. So they both converge. Kind of cool. I will point out, because I think it is worth pointing out, that in a very, very similar way, in fact, I'm going to encourage you all to do this on your own later. You can show that the sum from n equals 1 to infinity of sine of 1 over n diverges by doing limit comparison with 1 over n. And you get the same sort of result. It's just that now you're comparing it against something that diverges instead of something that converges. Kind of cool. I think it's really neat, actually. Yeah. Sure. Let's look at one more. One more. Yeah, we should try and talk about the ratio test. Yeah, we can. So one more example. Let's say we have sum from n equals 2 to infinity of 1 over the square root of n times the natural log of n. Natural log of n, dicey sometimes. Yeah. Okay. So my usual go-to with the natural log of n is to kind of pretend like it's like the square root of n. It's not exactly the same, but it's a good starting place. So I'm going to say, well, let's try to do a limit comparison with 1 over the square root of n times the square root of n, which is just 1 over n. I should really say the sum of whatever, which diverges. So using that, I'm thinking it might diverge. I don't actually know, though, if this converges or diverges. So that's what we're going to try. So if I do the limit, n goes to infinity of 1 over root n times natural log of n over f, and I left myself room to I didn't mean to do that, but fine, over 1 over n. Always, right, just as a reminder, always the unknown over the known. Then we're going to get the limit, then goes to infinity of n over the square root of n times the natural log of n. And before I try using L'Hopital's rule here, which is what I'm going to do because it is an infinity over infinity type, I should simplify this. N divided by the square root of n is just the square root of n. So it's definitely going to be in my best interest to write this as n to the 1/2 over the natural log of n. And now let's try using L'Hopital's rule. I don't actually know if this is going to work. It's just, this is the process, right? We try stuff until something sticks. Maybe you're going to do it wrong the first 2 times and then find the right way to do it. That's okay. A lot of this stuff is trying things that might not work. So using L'Hopital's rule, the derivative of n to the 1/2 is 1/2 n to the negative 1/2, and the derivative of the natural log of n is 1 over n. And then we should simplify, because if you try and write this like out, if I don't simplify this, I might be thinking, well, I've got a 1 over 2 times the square root of n over 1 over n. You might be like, oh, I have a 0 over 0 again, or I should not say again. I have a 0 over 0, and I'm going to use L'Hopital's rule again. No, I don't want to use L'Hopital's rule again. That's just going to get me down this never-ending chain of using L'Hopital's rule until the world ends. Instead, I should simplify. And that's almost always pretty good advice. Is if we can simplify the thing we're working with, we probably should. So we've got n over 2 root n, and that's just going to simplify to root n over 2. And that's going to be what? Infinity. Is infinity okay? Yes, because I'm trying to show what? Divergence. Infinity is okay for divergence. Because again, what that really means is we're saying this sequence is in some sense infinitely larger than that sequence. Since that sequence is has a divergent series, this sequence is also going to have a divergent series. Cool. All right, the ratio test. So much to say about the ratio test. What time is it? Yeah, we got time. We should talk about the ratio test. So the ratio test. Ratio test is probably my favorite. It's hard to have favorites, but the ratio test is really great because unlike other tests, you don't have to have an idea of whether or not the series converges or diverges. You apply a test, and then if you get a certain thing, you just know. So actually, let's save the test before we actually talk about why it works. So here is the ratio test to show, or I should say, for the series from n equals 1 to infinity of a sub n, find the limit as n goes to infinity of the n plus 1 term divided by the n term. And let's say that limit is equal to, people often use L. I like to use R for a good reason. Let's say that limit is equal to R. Here is what happens. There are three things that happen. If that limit R is less than 1, then the series converges. If that limit R is greater than 1, then the series diverges. And finally, unfortunately, sometimes this happens, if that limit R is equal to 1, the test is inconclusive. I want to point out, that doesn't mean that it doesn't like converge or diverge. It just means we don't know. It's kind of like getting that the limit is 0 of the sequence using the nth term test. It doesn't really tell us anything. It tells us, really what this tells us is, when someone says the test is inconclusive, what you should hear when you hear those words is, try something else. That is actually what that means if you're trying to find convergence or divergence. God, there's a lot of explaining to do as to why this works. Let's do an example first, and then we'll talk about maybe why this works. Maybe we'll talk about it next time because the explaining is a little bit much. So let's say we want to determine the convergence or divergence of the sum from n equals 1 to infinity of n to the 4th times 3 to the n plus 1 over n factorial. Now I'll say this definitely has the hallmark of a test that I should use the ratio test for. If you see a factorial specifically, you should almost always, so there's a couple of examples that don't, but almost always ratio test is where you go first. Maybe it won't work, but you should always try the ratio test if you see a factorial in your series. So we're going to do the limit n goes to infinity of a sub n plus 1 over a sub n, which is the limit as n goes to infinity. I'm just plugging in n plus 1 for every n. So it's going to be n plus 1 to the 4th times 3 to the n plus 1 is n plus 2 over n factorial. And I really don't want to write divided by a sub n. I'm going to write multiplied by the reciprocal. So there's my, oh, sorry, not n factorial, n plus 1 factorial. I forgot the n plus 1. See? And then I'm going to have times the reciprocal of that. So n factorial over n to the 4th times 3 to the n plus 1. So just so everyone's clear, right? Here's my a sub n plus 1. Here's my 1 over a sub n. And of course, I haven't really left myself enough room here. Then what I usually almost always do is I group all the similar things together. So I'm going to rewrite this as the limit as n goes to infinity of n plus 1 to the 4th over n to the 4th. And 3 to the n plus 2 over 3 to the n plus 1. And n factorial over n plus 1 factorial. And then we should simplify. So simplifying, n plus 1 to the 4th over n to the 4th doesn't really simplify. I mean, you could write it as n plus 1 over n all to the 4th. And I probably would. Almost always when you're using the ratio test, anything that's n to a power doesn't really contribute anything. It just ends up going to 1. And that's what's going to happen here. N plus 1 over n to the 4th power n plus 1 over n goes to 1, and 1 to the fourth is still 1. And then I can simplify this. 3 to the n plus 2 divided by 3 to the n plus 1 is just 3. And then n factorial over n plus 1 factorial, this is an important one, it comes up a lot. That's just going to be 1 over n plus 1. Just so everyone's clear, because it comes up often. If I did 4 factorial over 5 factorial, that's going to be 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. Oh yeah, all the things except for the 5 cancel out. And you just get 1 over 5, which is your 1 over n plus 1. And you could totally show the work you want. You could be like n factorial over n plus 1 factorial, and then say, well, I've got n factorial over n plus 1 times all the smaller things, which is and then those things. It happens a lot, so you definitely should get comfortable with it. And then finally, n plus 1 over n to the fourth goes to 1 times 3, and 1 over n plus 1 goes to 0. This is 0, which is less than 1. So this series converges by the ratio test. Something I left off, which is not a huge deal, but occasionally comes up, is technically the ratio test, you're taking the limit of the absolute values of n plus 1 over n. So really, there should have been absolute values around those, but everything was already positive, so it doesn't actually really matter. Here, later on, when we start talking about alternating series, sometimes we use the ratio test to show some stuff, and then you need to be more aware of the absolute values. Especially also when we talk about power series and interval convergence, then you absolutely need the absolute values. Okay. That's all I got for today. Monday, we'll talk more about the ratio test and then the root test. And I would also say, if you want, you can look at Grant's notes, which I'm really working from, just to kind of talk about why the ratio test works. It's really because what we're saying is essentially this sequence eventually is starting to act like a geometric series. And because you're saying each next term is just the previous term times some ratio. And if that ratio is smaller than 1, then just like with a geometric series, it converges when the ratio is less than 1. This series converges when its quote unquote ratio is less than 1. That's kind of the idea behind the ratio test, why it works. And very, very briefly. All right. Have a lovely weekend. Have a fun and safe picnic day.